Okay, next in our chapter of thermodynamics, we're going to talk about the relationship between heat and work. So, as long as a substance is not undergoing a phase change, remember the graph we looked at last time, as long as a substance does not go through the phase change, its internal energy, the energy of the particles, will increase as long as the temperature increases. Work can transfer energy to a substance, results in an increase of internal energy, and can be transferred to another substance as heat. Okay, so cause work happens, heat is created, and that heat is transferred to another. So energy can be transferred to a substance as heat and from a substance as work. So heat and work are both energy transferred to or from a system. Now I keep using this word system. What is a system? A system is a collection of matter within a clearly defined boundary across no matter passes. So if we're talking about, let's say, my laptop, if I include it all as part of the system, we're just talking about the laptop. We're not talking about the air, the environment around it. Same thing with the systems we talk about in physics. It's what we're talking about without the extra influence of everything around it. So the environment is everything outside the system that can affect or be affected by the system's behavior. We also call it the surroundings. Okay, so there's the system, and then there's everything else, the environment. All the parts of the system are in thermal equilibrium with each other before and after a process removes or adds energy. I keep saying on the previous notes that the objects are trying to get into thermal equilibrium. So you have a warm object, hot object, and a cold object. The heat is going to go from the hot to the cold until they reach the exact same temperature, and in that case, they are in thermal equilibrium and no heat will flow. So, how is work related to heat and internal energy? So, pressure is the force per unit area acting on an object. Okay. You can calculate it by pressure equals force divided by area, or F divided by A. It's going to be measured in pascals. In physics, there are other units, just like everything else has multiple units, but we're going to use pascals, which is Newton per meter squared. So Newton per meter squared. I'm sure you've heard of some of these other ones in pounds per square inch, PSI. We use that here in the United States. You've heard of bars if you've listened to the weather report. Other units are ATM, atmospheres. Okay, we're going to use pascals. And this pressure this force is caused by particle collisions. The particles are hitting into things, and that is what causes pressure. So work done or by a gas is the pressure multiplied by the change in volume. Okay, so work is force times distance. We already knew that from a previous chapter. Work is force times distance. So work of a gas will be the pressure times the change in volume. So pressure times the change of volume. Change of volume, we're drilling down here, is the area times the distance. Change of volume, area times the distance. Make sure all three of these ends up in your notes because you will be using them. So if a gas is compressed, delta V is negative. Okay. So work is done on the system. If the gas expands, delta V is positive and work is done on the system, because to do work, you have to have a distance change. So if it's compressed, delta V negative, work is done because there was a change in the volume. If gas expands, delta V is positive, work is still done. But if the volume remains constant during the process, no work is done because there was no change in distance. So, an example. An engine cylinder has a cross-sectional area of 0.010 meters squared. How much work can be done by a gas in the cylinder if the gas exerts a constant pressure of 7.5 times 10 to the 5th Pascal on the piston and moves the piston a distance of 0.040 meters? So here are the givens. Here's the area. Here's the distance in which the piston is moved. Here is the pressure, okay, in pascals. Remember, a pascal is a Newton meter squared. We need to find the change of volume in order to find the work. So, change of volume is area times distance. So, here's your area times the distance it moved. So your change of volume was 4 times 10 to the negative 4 meters cubed. Okay, volume is cubed. We plug that into our work equation for gas. It's pressure times the change of volume. Pressure times change of volume. So here's our pressure, and here's our change of volume that we just calculated. And what you should get is 3 times 10 to the second joules. Remember, work is in joules. So, work, internal energy, and heat are all related. In an ideal thermodynamic process, not every one of these is going to be present, but they are related. No work is done in a constant volume process. So there's 3, but if you're missing work, so that means there's no change of volume. We call this process isovolumetric, a thermodynamic process that takes place at constant volume, so that no work is done on or by the system. Okay? So if there's no volume change, there's no work done, and we call it isovolumetric. Iso means same, volumetric, volume. Same volume. If internal energy is constant, that means the temperature did not change. If the internal energy is constant, it is an isothermal process. Iso, same, temperature, same temperature. So a thermodynamic process that takes place at constant temperature in which the internal energy of the system remains unchanged. Okay. So this would be a balloon that is in thermal equilibrium with its surroundings. Okay. A storm comes up, the barometric pressure goes down. Air pressure goes down right before a storm. The balloon will react to that that reduction of pressure in the air by the balloon will get bigger. Okay? As the pressure drops outside, the balloon is going to try to get in equilibrium pressure-wise with the environment. So it will get bigger. Okay? Temperature hasn't changed. So it's an isothermal thermal process, same temperature. Okay, so what if energy is not transferred as heat during a process? We call that, and this is a mouthful, adiabatic process, a thermal process during which work is done on or by a system, but no energy is transferred from or to the system as heat. Okay, and we're going to talk about these more next time when we talk about refrigerators and internal combustion engines. Okay, so no energy transferred, it's adiabatic process. And that's it. Get your notes written, get them in your journal, take a picture, and send them to me on Schoology. Thanks, guys.